Thank you. So I'm back, part 2 of 3. This one is, as Matt said, an update on a research center called CSAFE. There were some references to research happening in CSAFE. CSAFE stands for the Center for Statistics and Applications in Forensic Evidence. I'm going to describe CSAFE in a little bit more detail. The slides you're looking at are actually part of, I think it was just last week, time goes fast, had a site visit from NIST, the National Institute of Standards and Technology, which funds CSAFE, last week. So these slides kind of were for them to review our progress. CSAFE has been in existence for 4 years, initially funded for 5 years, so we have one more year, and they're in the process of evaluating our work to date to determine whether additional funding should be provided. So a little bit, this is 5 years ago, there was a call put out by NIST to create a center of excellence, a NIST center of excellence, focused on probabilistic analysis, especially in pattern evidence and digital evidence. And here are some of the tasks they were looking for a center to do. I should mention a couple of things. In the academic world, we distinguish between grants. In a grant, I write a proposal to a funding agency to say, I'd like to do research on fingerprint analysis or whatever it might be. If the agency is convinced that I have good ideas and have the ability to execute, they will give me the money to carry out the study. And their participation will stop there. And then I'll do my work. I may decide fingerprints are no good, and I'm going to work on shoe prints instead. The granting agency, if they feel I've gone too far, can act on that, but generally won't. That is, they fund the person to do the task and let it go. CSAFE is not a grant. It is what's called a cooperative agreement. So NIST formed this to help NIST. So they wanted us to do things to complement what's happening at NIST, to collaborate with NIST, and the like. So that's very important. The projects that we do are all vetted by a conversation with NIST. We say, we have researchers who want to look into this, and NIST either says that's a good idea. They might say, we've already got people doing that. We'd rather you use your expertise in another direction, or collaborate with us on that. On several projects we proposed, they said, we really want you to focus on pattern evidence and digital evidence, and that's not either of those, so please don't do that. And so we didn't do that. Okay. On this slide, what I want to say is basically we have our research in the center, research written broadly, organized in several categories. The 2 categories that are obvious from the call, we have projects on pattern evidence and projects on digital evidence, as you might expect. But we also have 3 other categories that I would describe, and I think they're relevant for the people in the room. Well, the first one's only relevant for me. Statistical foundations refers to statistical research on ideas, like likelihood ratios and some other things that will come up this afternoon, that apply broadly across evidence types. So they're not specific to a single discipline, like fingerprints or shoe prints. The 2 other things that are listed here are interesting. Human factors refers to a wide range of topics that are associated with the human element of carrying out the analysis. So this, for us, we take a very broad view of this. It includes things like proficiency testing and what that means and how it might be done and how it might be analyzed. It also refers to quality control in labs, things like that. So we have a number of projects in that space. And the last area we have it, which you wouldn't necessarily call research, is we have projects focused on training and education. So that, in fact, we use CSAFE funds, and several of us in the center go around and do trainings and workshops like this. So that, in fact, CSAFE is paying for me to be here to do the presentations that I'm doing today. I have done this at forensic labs, both locally where I live. I gave 2 half-days to the Orange County Crime Lab. All the examiners on different disciplines all came together, and we went over some of the probability and statistics. But I've also traveled to Seattle, Virginia, several other places, colleagues of mine in Missouri, and so on and so forth. And so we're very excited about that. And if you are a lab person or involved in some organization of lawyers or otherwise, and would be interested, this is something we do. We cannot meet all demand. That is, demand is great once you kind of establish that you can do this. But it is something we do. It is something NIST has supported us doing, feeling like that's an appropriate use of NIST dollars to help transfer the technology, in this case, the statistical technology, out to the community. And I should have actually said that my first remark today. When I go out and give these presentations, my goal is not to turn anybody in the room into a statistician. That's not at all a realistic or a desired outcome. My goal is to really create a common terminology, and that's why I give virtually the same talk to practitioners in the lab, examiners, to lawyers, to judges. I'd like us all to have the same language on which to decide what the appropriate techniques and tools are. So, as I said, those are the kind of 5 areas. What I'm going to describe now are some of the progress, primarily in the pattern evidence. Okay, and in fact, I think it dovetails nicely with the previous session. Daniel talked about firearms examination as carried out, which is really expert opinion based on training and education, and made several references to fancier technologies coming down the pike. And in fact, the PCAST report, which we'll hear more about later, had several recommendations, but one was a pointer towards someday getting away from expert opinion towards more quantification of the evidence. And the first project, I'm not quite ready for the first project, so let me stop before I get to the first project. What I wanted to mention is the slides that you had that I'm looking at actually have basically short descriptions of up to 30 projects. I'm not going to do all of them. I'm going to do one in detail and kind of talk about some of the things. But I told you how we categorize the projects into research areas. But I also would like to say that the way that we think we're contributing is in a number of different ways. So first and foremost, the thing that we're most excited about at some level as statisticians is trying to develop these novel objective quantifications of forensic evidence. So that's several of the projects are about that, and I'll talk about one in a second. But we're also interested in statistical analyses that look at existing methods and how they work. If you will, you can think about the black box studies that PCAST recommended as being an example of this. I've been involved in projects that look at the reliability of handwriting experts judging signature complexity, for example. One of our investigators, and this is extremely relevant to the second part of what we just heard, one of our statisticians partnered with, he's at Carnegie Mellon, partnered with the Allegheny County Office of the Medical Examiner. They were curious about lifting fingerprints from drug bags. And their existing practice was to have the fingerprint examiner transfer the drugs out of the bag into another storage device, and then lift fingerprints from the bag. And they were concerned about that practice, but they didn't know anything better to do. And in collaboration with one of my colleagues, they did some studies that showed, in fact, if you treat the bags with the drug in it, using the chemicals that are used to raise the fingerprint evidence, they found that they didn't affect the contents of the bag. They didn't affect the weight of the contents in the bag, and that therefore it was practical to lift fingerprints from the bag without transferring the drugs, which was much safer for everyone. So that was kind of an immediate practical kind of impact of CSAFE research project. Most of the projects have a longer time frame than that. So we do that kind of thing. The other thing that we're trying to do is develop publicly available data. That is, to develop novel objective methods, you need test cases to work with. And a problem for many people trying to get into research in forensic science has been the absence of publicly available data. The FBI has an enormous database of fingerprints, but for obvious reasons, they don't make it publicly available. But what is available then? If you want to do a new method for firearms, what data do you have? NIST is developing a database, but to date, there's been very little data. So we're trying to develop data. And the other thing we're trying to develop, which is relevant to some of what we just heard, is we believe strongly in open source software. That is, for making the software available. This has been an ongoing issue in the DNA world, the mixture DNA. You have proprietary software. You have two different proprietary softwares giving two different answers, and it's a real issue. So the research that we're doing, we're releasing the software. It's a very touchy issue in the forensic community, especially because, federally funded research. The goal is at some level to also develop industry out of federally funded research. So anyway. So those are different things we're doing. What I'd like to do, I don't want, as I said, I could go on for an hour on these sets of slides, but I wanted to describe one project in some detail, and then maybe talk about a few of the data and software issues. So I'm not an expert. This is not my specific project. It is colleagues of mine. But as was mentioned in the last session, there are different kinds of firearms evidence. What I'm going to talk about are the firearm striations on the lands of the bullet. So what you see here are a picture of a bullet from two different profiles. The top is kind of looking at the bottom of the bullet. And you see, not necessarily well, but there's grooves and lands. And so as the bullet goes through the firearm, only part of the bullet surface comes in contact with the barrel of the gun, and that's the part that they study the lands. So they have the land impression between two grooves. And you have a picture here, which is kind of, the bottom picture is the side of the bullet. And Jim asked about, could you use facial recognition? This is kind of the 3D image, part of the 3D image from this part of the bullet. And you see some of it doesn't come off well, and some of it comes better. And you would have two of these for a crime scene bullet and a bullet test fire, and try to decide if they're the same. So the approach that we're using is not making full use of the 3D-ness of this. It's taking a slice across. Okay, so now you're back to 2D, got rid of one of the Ds, and you get a picture like the one above it, okay, which is one land, and what's happening here is you have the striations on a land. These two things here are basically the shoulders, that is where the grooves separate the land. And so there's a lot of analysis that goes on to take this thing that we can measure and smooth it out, because it's very noisy, cut off the shoulders, they call it, phase 2 and phase 3 here. And then there's still a lot of stuff happening here. You can't see it, because it's dominated by the curve. When you look at that picture, you see the curve. But if you subtract the curve out, you end up with something like this. And so my collaborators call this the profile of the land. So that's kind of the data that comes out when you do this. Each bullet has 6 lands. You get one of these for every land, and the problem becomes matching, right? You have a bunch of lands, and do some of the lands match, things like that. Not the best picture, and I apologize for that. What you see there are 2 lands laid on top of each other. And so the goal is to decide if they're a match or not a match. And you can do that by using some of the features that were mentioned earlier in the exam. We had Daniel mentioned consecutive matching stria. When they do it on a microscope, you have these 2 images next to each other, and you literally try to count how many striations you see that continue across the divide from one image to the other. That, in this context, would amount to looking for peaks that occur at the same place. Those would be the same striations. And so you could count the longest string of consecutive matching peaks. Or you can actually just correlate those 2 curves. So there are a bunch of measures. The approach that my colleagues are using is not any one of those measures, but combining all of them using some of the modern, you had black magic. We have, machine learning magic, artificial intelligence magic. You've all heard about all these buzzwords. But they're basically sophisticated algorithms for taking a bunch of features, things like this, and associating with them with match or not match. So the way that they built this classifier is they have a bunch of cases where they know the answer. This land matches this land because they came from the same gun. So they have a bunch of cases like that, and they have a bunch of other cases. In fact, there's lots and lots of cases where this land does not match this land because they were fired by different guns. Because what happens is if you do this with 10 guns, 10 bullets and 10 guns, you only have 10 matching pairs, but you have like lots of non-matching pairs because this bullet did not come from any of the other 9 guns. So you can kind of get lots of comparison. So they train this algorithm to build a classifier that now all you need to do is get the features, get the 2 profiles, compute the features, put it into the black box.
And people may be familiar with decision trees. Could you explain what a random forest?
Yeah, I'm not going to go into great detail, but those of you who had some statistics, some familiarity with statistics, may be familiar with kind of regression. Regression is a very well-known statistical tool. The way regression works is it relates some outcome, in this case match or not match, to some set of predictors or features. So it's a great technique. It works very well, but it's very limited. It's a very strong assumption to make regression work. An alternative that's been around for actually a long time is the idea of using a decision tree. That is to say, if the number of consecutive matching stria is greater than 10, it's more likely to be a match. And beyond that, even among all the ones that are bigger than 10, let's look at the correlation. If the correlation is bigger than 0.7, more likely to be a match. Less than 0.7, no longer. So you can actually build a tree of decisions like that. And that is an alternative to regression for building a classification rule. And as the name might imply, the random forest idea builds on the tree idea and says, gee, if a tree is a good idea, more than one tree must be a better idea. And so that's the forest idea. It requires more detail and something, again, perhaps a future presentation. But so that's what was done in this case. And when you do that, out of that tree, forest actually, because a tree would just give you one answer, a forest gives you lots of answers. The horizontal axis here is a score that's associated with a given pair, and you can think about it as the probability that that pair corresponds to a match or not. And you see 2 blobs here. The blue blob are cases where we know in fact that these are matches. And you'll notice they have very high scores, above 0.5 typically. The gray are cases where we know they don't match. They were not fired from the same gun, and they have very low scores. And so the idea is this becomes an automatic technique for taking in 2 lands, computing their profiles, getting their features. At that point, you just plug it into a formula, and out comes a score. To software, and out comes a score. And in doing this, they estimate their error rate, their misclassification rate, as being less than 1%. One half of 1% are the number of times they would misclassify same source pair as non-same source or vice versa. Interesting, so when you see stuff like that, I'm personally very skeptical, even of my colleagues. That is, it's really hard to believe that because what happens is it works really well on the set of data you teach it from, but will it work outside? And that work is just beginning, but it's incredibly promising. I've been actually blown away. So my colleagues have talked about this, and the Phoenix Police Department agreed to do a study. The Phoenix Police Department sent them 8 weapons and 10 bullets, and that's all they were told. They didn't know if the bullets came from those weapons. Some bullets came from some of the weapons. They didn't know any of that when they analyzed it. And they used the tree they had already built on other guns. So these are totally new weapons, not seen, okay? This picture is a little confusing. What you've got are, across the top are the guns. There are 8 of them. Each gun had 3 test fires. So we know that those bullets came from those guns. So there are actually 24 columns. 3 test fires from each of 8 guns. And the rows are the bullets. And so what was done? Each bullet was compared with each of the 24 test fires. And we get out a probability from it. And that's, the probabilities are coded here. So gray is a very low probability of being a match. Orange is a very high probability of being a match according to this algorithm. So if you take the first bullet, N, it has very high scores of being a match with the 3 test fires from gun A9. It has very low scores with the other 21 test fires. I wouldn't be telling you the story if bullet N was not fired from A9, right? Okay. So, and what you see here is there are 7 bullets that were matched to 7 of the guns, and those are all correct. The 3 bullets at the bottom, which were not matched to any guns, were in fact not fired by any of those guns. And you'll notice the last gun did not fire any of these bullets. And they were not told any of that. They did not know the possibility. So this is really, to me at least, very impressive. It's just one study, it's small, but it's very impressive, and they're doing more of this kind of thing. Oh, okay. Oh, that was me, I think. Anyway, well, it's not me. Okay, so I don't really have much time, so I just wanted to say, as part of this, we're collaborating with a lot of places. And so CSAFE is highly collaborative. We have a very, very close relationship with the Houston Forensic Science Center. For those who don't know, Houston set up independent forensic science center, so it's not part of law enforcement. And for that reason, they've been relatively easy to collaborate with. We actually have a CSAFE hired person embedded in the Houston Forensic Science Center to help with data collection in a variety of studies and the like. But we also work directly, as you saw, with the Phoenix PD and with others. At this moment, we've built up a large database. I should have said this. The center, it bought 2 of the 3D microscopes that Daniel mentioned. So they're very expensive. They got a grant from a foundation for one of them, and the grant itself bought the other one. And they have a bunch of undergraduates trained to generate the images. They're not trained fingerprint examiners, but they're trained to generate the images. And so we've collected 25,000 of those lands. There's 6 per bullet, so maybe 4,000 bullets or something like that. And again, these data sets are to be made public. Okay. There's an ongoing study of persistence. The speaker in the last session mentioned, you know, you get this unique profile from a gun, and it's good and it stays and so on. So they're studying, does it really stay, by getting bullets every 50 for 2,000 bullets. Can you really do that? They've always mentioned the 10 consecutive Rugers, and it's very powerful evidence, but it's just one piece of evidence, and so we're trying to add to that. We work in a lot of different areas. I don't have time, nor probably the inclination. We're trying to develop shoe print data. They actually did an experiment at Iowa State where they gave shoes out to people so they could have them wear it and take multiple images of those shoe prints, and those are also being made public. I think, let me see if there's anything else worth talking about. Bloodstain pattern, I suspect. So there's a lot of research projects, but again, one of my collaborators at Iowa State, bloodstain pattern analysis is very tricky to work on as a scientific enterprise. Why? How do you get data to work on, to build methods? Right now, it's, again, expert opinion. No animals or humans were hurt. No, animals were hurt. They used pig blood, and a colleague of mine basically set up an apparatus to create different kinds of blood-stain pattern images. And again, made those public, which now facilitates research. So that's a little taste of what CSAFE is about. I'm happy to talk more if people have questions, but please feel free to reach out to me, and I'd be happy to talk more about it. So thank you.
It's time for lunch, so